Hello and welcome to this video about metals. We're going to look at different properties of metals, bonding in metals, and then we'll look at some specific metals, the alkali and the alkaline earth metals, and the transition and inner transition metals. As you already know, most elements are metals. The metals are indicated by this kind of a yellowish color here. All of these and these are all metals. There are only a few elements that are metalloids, and then we have these that are non-metals. Properties of metals. Metals are lustrous. That means they're shiny. Metals are malleable. That means they can be hammered into a shape or into thin sheets like these copper sheets. Metals are ductile. Means they can be drawn into a wire like these wires here. Metals are also good conductors of heat and electricity. How do metals bond with other atoms and other kinds of elements? Well, metals can bond with non-metals, and in that case, let's look at an example. Let's take the metal sodium. Sodium comes from right here on the periodic table. It lies within the alkali metal family right here. And so all of these, remember, have one valence electron. So here we draw sodium with its one valence electron. What about chlorine? Chlorine is a non-metal. It comes from clear over on this side of the periodic table. It has 1, 2, 3, 4, 5, 6, 7 valence electrons. It's a halogen. And so we draw the 7 valence electrons around the chlorine. Now, what happens when these two get together? Well, chlorine would really, really like to have a full octet. It would like to have all of its valence electrons at the number 8, nice and full. So would sodium. And if you look at where chlorine is on this periodic table, it only has to gain one more electron, and it could have that stable number of electrons like argon. It would mean that it's this third energy level, really, is full, and it would be complete, and it would be very stable. Sodium, on the other hand, it would be much easier for sodium to simply lose that extra valence electron. So what happens when these two get together is that sodium basically gives its electron up, chlorine takes it away. So we end up with the chloride ion having a -1 charge because it has one extra electron, one more electron than it does numbers of protons, and the sodium ends up with a +1 charge because it's lost one of its electrons. Sodium chloride is also known as table salt. Metals can bond with other metals as well. If they do that, it's called metallic bonding. And in metallic bonding, positively charged metal ions, because metals tend to lose electrons, and they become positively charged ions. They're surrounded by a sea of electrons, and that's what ends up happening in a metallic bond. So let's take a look at some of these individual elements. Let's look at this family, the alkali metals. It comes from right here on the periodic table, specifically lithium, sodium, potassium, rubidium, cesium, and francium. And they are like the other metals. They're shiny, malleable, ductile, good conductors of heat and electricity, but the alkali metals tend to be soft and softer than most metals. They do react very rapidly, sometimes violently, with oxygen and water. Here's an example of potassium reacting with water. Because they are so reactive, they do not occur naturally in elemental form. And part of that reason is that they have that one valence electron. Makes them really want to lose that electron to have that stable, full outer valence shell with their electrons. Sodium and potassium you will recognize because those are necessary for living things, living organisms. Lithium can be beneficial as well to living organisms. Rubidium and cesium are sometimes used in light detecting sensors. Cesium, one of the isotopes of cesium, is radioactive, meaning that the nucleus breaks down and gives off very high energy particles. So sometimes it's used in atomic clocks. Francium is also radioactive, but it is extremely rare. It's estimated less than 30 grams of francium are in the Earth's crust at a given time. Let's take a look at the alkaline earth metals. They come from this second group on the periodic table, and when we look at those, we have beryllium, magnesium, calcium, strontium, barium, and radium. And they are also reactive. They, however, have 2 valence electrons, 2 electrons in their outermost shell. Some of these are used to color fireworks. Magnesium makes a very, very bright white light. Also, the oxide of barium will make a white light. Calcium in fireworks will give an orange color, and strontium gives a very nice red. Additionally, some of the alkali metals give nice colors in fireworks as well when they're being burned. Lithium is a really pretty bright reddish color, and sodium produces a yellow. Magnesium is a metal that's used in a lot of different uses. It's in cars and planes, even softball bats. It's also really important in life. It is a part of the chlorophyll molecule, and we know that's critical for all life here on Earth as well. Calcium is not very often used as a metal, but it is essential to life as well, and organisms use calcium. Barium is sometimes used to diagnose digestive disorders because it absorbs X-ray radiation really well. Radium, the last element in this group, is radioactive, and it's often found in association with uranium. So now let's take a look at the transition elements. When we look at the periodic table, oftentimes we'll call this group 1 and group 2. This will be group 3. The transition elements are groups 3 through 12, and they're considered to be in transition between the main group elements, and we call the main group elements the alkali, alkaline earth, and then groups 3 through 12 here would be considered the main group elements. The transition elements have varying numbers of valence electrons. We're not going to go into that right now. And we're just going to look at a few of the transition elements. Here's iron right here, cobalt, and nickel. If we take a look at those 3 metals, sometimes they're called the iron triad. They're the most common magnetic elements that are used in steel and other metal mixtures. Iron is the main component in steel, and sometimes nickel and cobalt are added to give it different characteristics. Nickel is also used to give a shiny protective coating to other metals. Some very beautiful elements here in the transition element category are copper, silver, and gold. We can find those right here. In group 11, there's copper, silver, and gold, and they're once used to make coins because they are very stable, malleable, and they can be found as free elements in nature. Because of the rarity, we don't always use those to make coins anymore. We now add a lot of nickel and zinc to the coins that we have in our country. Copper is used in electrical wiring because it's a really good conductor of electricity and fairly low cost. Silver and gold, obviously, they're used in a lot of jewelry because they're very beautiful and they're also rare. Let's take a look at zinc, cadmium, and mercury. They are found in group 12 of the periodic table here. Zinc and oxygen in the air, they combine to form a thin protective coating of zinc oxide on its surface. So oftentimes zinc and sometimes cadmium also will be used to coat metals like iron to prevent them from rusting. Also, cadmium is used in rechargeable batteries. I'm sure you recognize that. Mercury is the only metal that is a liquid at room temperature. It's rarely used in modern thermometers because it's also very toxic. Now let's take a look at the inner transition metals, the lanthanides and the actinides. If we were to stretch out the periodic table and we were to cut in between groups 3 and 4 on the periodic table and insert these inner transition metals, the periodic table would look like this. It would be very, very wide and hard to read. So often these are cut out and simply listed down at the bottom. The first row are the lanthanides right here. And they're called that because they follow lanthanum, the element lanthanum. Lanthanum, cerium, and praseodymium, and samarium as well, are used with carbon to make a compound that's used extensively for movie lighting. Europium, gadolinium, and terbium are used as colored phosphors. Remember, phosphors change ultraviolet light into visible light, and televisions once used these compounds to produce colors. Element number 89, right, it's right there, is called actinum. So elements that follow that, 90 through 103, are called the actinides. All of them are radioactive and very unstable. Because of their instability, they're also extremely rare or non-existent in nature. It's also really hard to research them because they are so rare. Thorium and uranium, here's thorium, here's uranium. They are the only actinides found in the Earth's crust in any kind of a usable quantity. However, they are pretty rare. Thorium is used in making camera lenses because it bends light without very much distortion. And everyone probably knows uranium for its use in nuclear reactors and in weapons. Here's some advanced ideas. Look at some of these man-made actinides. How are they formed? How do we make them? And how long are they stable? Which metal is used in the galvanizing process? And what's the purpose of this? Alkali metals each have one valence electron, so they form a +1 ion. The alkaline earth form +2 ions. But many transition metals have multiple different numbers of electrons they can lose when forming bonds. What are some of the ions formed for the different transition metals? Maybe you have some questions of your own that you'd like to research. Look those up, and I look forward to seeing what you come up with. We'll see you in class.